Instruments, Section 2. Please delete the slide on piston engine tachometers. Yes, the whole slide. Temperature measuring instruments. First, I'll go over the ones that don't require electricity. Let's just say we take two pieces of metal and twist them up into a coil. There's one. And let's take the other one. And we twist them up together. And let's tie one end down. Let's tie this end down inside of a tube. And this tube, of course, will have some holes in it. And on the end here, we'll put a needle and a gauge. And we'll calibrate it. If these two different pieces of metal are dissimilar, then they'll have a different coefficient of expansion. And if we hold this end down, as these two pieces of metal get hotter or colder, they'll either try to wind or unwind, and this needle will either go to a higher or a lower position. And that's very common for outside air temperature gauges that stick out into the windscreen. I think our PA44s have this exact kind of system. You can also use expansion of a fluid. This also uses coefficient. Of expansion, but now instead of coefficient of expansion of a solid, we're doing coefficient of expansion of a liquid. Let's say that we have a piston engine, 4-cylinder 172 engine, and we want to know what the oil pressure is. So we put a tube in here, and we run this tube all the way to a gauge inside the cockpit. And you'd say, okay, let's try again. We want it to be oil temperature. The fluid inside of here, is methyl chloride. And it has a very high coefficient of expansion. So when engine oil goes past it and warms it up and it gets hot, then it expands. And so the fluid in here, if there's no air in there, then when the fluid expands, it'll cause the pressure to go way up. Now you're going, wait a minute, Mr. Johnson, I thought this was oil temperature. Well, what we have in here is a board-on tube. And a board-on tube was just a regular cylindrical tube. Tube that's cylindrical. I think that's redundant. That was flattened out. And bent into a curve. I got a picture here. Then I guess I better get rid of all that other stuff. And we hold one end down, and we pump oil, or in this case methyl chloride, into it. And this tube, you can see that it's oval now. It's flat. When it gets pressurized, it tries to straighten out. So this curve tries to straighten out whenever the pressure goes high. Pulls up here, pulls this gear teeth down. Here's these teeth right here. And we have a big, giant needle, except we label it oil temperature, because the temperature in here is being changed because of higher or lower oil temperature inside of the engine. And this is a very common system on single engine recips, because we can have the engine and that board-on tube straight to the back of the instrument panel, or have that that little tube, not the board-on tube, straight to the back of the instrument panel. and it doesn't take any moving parts except for the gears inside of the engine. Lots of electrical systems for measuring temperature. First one is DC temperature indicating system. And here's a schematic. You might want to hit pause and draw it. You'll notice that we've got our DC bus, 14 or 28 volts. We're not going to worry about a circuit breaker. And it goes through this coil. It goes back to ground. So whatever's powering the circuit, whether it's a battery, you don't worry about drawing the battery in. Then electrons will leave the negative side of the battery, go through this coil to the bus and to the positive side of the battery. And it'll have lines of flux. So we'll have lines of flux. Now if it's got a fixed resistance, no, you've probably never heard of this, but E over IR. If we have a constant volts, and it's relatively constant, and we have a constant resistance or ohms, then we're going to have constant amps. If we have constant amps, that determines how many lines of flux is going to be. So constant amps is going to give us constant flux. So that's going to give us a certain strength of an electromagnet. However, we also have a path for electrons to go through this variable resistor. So here we've got a coil. Here we have a coil. And in here we got a permanent magnet. So these electrons, some can go through from the battery or the generator through the variable resistor and through this coil, but now to positive and then through the battery and back around. But this variable resistor is going to change the resistance. So now we don't have a constant ohms anymore, constant resistance. We've got constant voltage, but we have a varying resistance, varying opposition to current flow. So amps, it's supposed to be an I. So we're going to have a varying amps, and that's going to give us varying amount of flux. So the flux line, the lines of flux from this other coil here is going to vary. Now if we have a north pole and a south pole and we got a spring here, it's going to tend to pull the needle down unless the coil over on this side is stronger. So whenever the variable resistor has less ohms of resistance, more current will flow through this coil, it'll be stronger and move it back in the opposite direction. If there's less electrons going through this resistor, this will be weaker, and this coil on this side will pull it over. So the needle is going to vary based on which coil is stronger, and if one coil stays a constant strength and the other is varying, and we have variable strength electromagnet based on varying amps because of varying resistance of this variable resistor, then if we vary the resistance, we can change the needle movement. Now this is a very specific type of variable resistor, and it's called a thermistor because it uses temperature to change its istor, to change its resistance. And so we can stick oil through this. We can run oil past it or anything else, and as it heats it or cools it, more or less resistance, more or less lines of flux, more or less amps, more or less lines of flux, and the needle will move. So let's see if I can label this. So we're just going to call it a variable resistor. And we have two coils. we got a permanent magnet. And we got our DC bus. And here's our gauge. And we got a little spring pulling the gauge back to 0. And oh wait, I guess we could have a ground. So please be prepared to draw this diagram off the top of your head when I say draw a DC temperature indicating system, and then label it all. Oh yeah, and we got a ground over here too. There we go. There's also the thermocouple type of temperature indicating system. And the thing about a thermocouple type temperature indicating system is that it doesn't require electrical power by the aircraft. The DC temperature indicating system needs aircraft power. This system, no aircraft power. And here's the diagram. I'm sure you'll be able to draw it for me on the test and label it. This right here is the thermocouple. The thermocouple is two dissimilar metals, but instead of worrying about the coefficient of expansion, when one metal comes up and touches the other, right at the point where they touch, whenever it gets hot, one will give off more electrons. It will actually produce electron flow, amperage, and voltage. Of course, it's millivolts, which is thousandths of a volt. And it produces DC. So we can run electrons through a coil again and create lines of flux. And if this is the North Pole, this is the South Pole, and we've got a permanent magnet in here, and this is the South Pole and the North Pole, and again we'll have a little spring trying to pull the needle to 0. If more amps go through this coil, it'll get stronger. South and north attract, and it'll pull the needle over. So the hotter the thermocouple gets, so hotter the thermocouple, that leads to greater amps. That leads to greater flux in the coil, and that leads to greater pulling on the permanent magnet. So here's our permanent magnet, and there's our spring. And you'll notice I have a complete circuit here. We typically do not use the ground of the aircraft for one of them because the resistance here, since it produces such a very small voltage and therefore a very small amperage, the resistance, how much the resistance is critical, and to control it, it's going to come with its own set of wires to hook up the thermocouple versus the gauge. And here's what the thermocouple looks like. It looks like, this is the thermocouple right here. It looks kind of like a tall house, and it looks like there's a chimney on the side that fell down. That's what the thermocouple looks like. Thermocouple, I already got the spring and the permanent magnet and the coil. Yay! Measuring movement of something. You can use a DC remote position indicator. Here is the schematic for a DC remote position indicator. Oh wait, Mr. Bill. Whoops. Can't even spell variable resistor. Variable resistor, but in this case, instead of having a thermistor where the resistance changes with the change in temperature, we're going to have a knob. It's going to be just like the volume control on a stereo or on the volume control on a comm radio. This is just going to be, it's going to look like a circle, and it's going to have a shaft sticking out. If we hook that shaft up to, say, a flap, whenever the flap goes up or down, then this is going to get rotated. This is going to rotate and change resistance. Of course, we're going to take power off of the bus bar again. And so the theory of operation of a DC remote position indicator is identical to that of a DC temperature indicating system, except the variable resistor, instead of having it change its resistance based on temperature, we're going to have it change its resistance based on rotating a shaft. Be prepared to draw a DC remote position indicating system and label it identically to a DC temperature measuring system. Make sure you can do that for the test. Then there's alternating current. You're going to be flying those transport category jets, big biz jets, big turboprops, and big turbine-powered helicopters. You're going to have a lot of alternating current available, and so you're going to use a different system very commonly. There's going to be alternating current, and this alternating current goes to this coil, and the exact same alternating current goes to this coil. So whatever occurs in one coil is going to occur in the other. Of course, we have that sine wave. Let's try again. Got the sine wave with alternating current, and of course, if this is time versus amps, and we increase the number of amps, we're also going to increase the number of lines of flux. So every time the lines of flux expand, they're going to cross a wire. So we'll have electromagnetic induction. Lines of flux crossing a wire gives us a current flow. The current flow in this one wire, the current flow in this coil right here, it's hooked up in parallel to this wire right here. So everything that occurs in this wire occurs in this wire. So if we push amps through in this direction, it's going to push amps through in this direction. Well, I guess it'd be the exact opposite direction. So whenever these lines of flux cross this wire and induce a current flow, of course, if we have a current flow in here, we're going to get lines of flux off of it. And of course, we already had lines of flux off of this one, just like we did off of this coil. So these lines of flux here are going to affect this coil. These lines of flux off of this coil are going to affect that coil. So you're going, what in the heck are you talking about? Okay, what in the heck am I talking about? This coil right here is going to get hooked up to something, say maybe a flap. Whenever the flap rotates, this coil is going to rotate. And so it's going to affect these three coils differently, but each of these three coils is going to have the same current flow as this one. So as this coil rotates and affects the outside coils here are going to affect the inside coil and push it around through lines of flux pushing each other. And this right here is the needle. This side here is the gauge. And this right here is the sender, or the transmitting unit. And it doesn't use how many amps. If these wires are all really, really long and the current flow is lower, that's okay, because the current flow here will be low, the current flow here will be low. It'll still be very, very accurate, even though we have really, really long wires. And that is a downside for our DC remote position indicating system, is this wire. The longer it gets equals higher resistance, and the accuracy of the gauge won't be as good. So this might work out 20 or 30 feet. But what if we have something on the tail of the airplane and the wire ends up being 200 or 300 feet? So the negative or a disadvantage of the DC remote position indicating system is that the longer the wire, the less accurate it is. The nice thing about the AC remote position indicator system, the AutoSyn or the Magnuson system, is that we can have really long wires and we have a really, really, really high accuracy because it's not based on amps and resistance. And the Magnuson system and the AutoSyn system are extremely similar. You're going to find them all over the place on aircraft that have alternating current as their primary power system. You've probably seen a magnetic compass. You probably already know that magnetic variation is essentially the difference between the angle of pointing to the North Pole and pointing to the South Pole. Here's a really nice chart. Let's say we're down in here. Let's just say it's 12 degrees east. And here's the magnetic North Pole. Here's the magnetic North Pole. It's on an island, Bathurst Island. Magnetic North Pole. And the true North Pole, it's way up on the axis of the Earth. So the angle pointing to the North Pole and the angle pointing to the magnetic North Pole, this angular difference is 12 degrees. And essentially, if we're looking at true North Pole, we'd have to look slightly to the east to find the magnetic North Pole. If we were way over here, for instance, here, this is the zero isogonic line. It's called the agonic line. Let's say you were here in the middle of Kentucky, it'd be a straight shot, so we'd have 0. If we're over here in New York City, where they make really good salsa, and let's just say it's 18 degrees west variation, it means that if we looked at the North Pole, magnetic North Pole is over here, we would have to go slightly to the west to find the magnetic North Pole, hence the west variation. What I find cool about this chart here is you can see where the magnetic South Pole is. It's pretty much due south of Australia just before it gets to Antarctica. It's actually out in the middle of the ocean. Of course, the things that's different from deviation, magnetic variation. We can calculate the difference between where the angular difference between the true North Pole and the magnetic North Pole. Deviation, on the other hand, are things that cause the compass to point at some place other than the magnetic North Pole. Usually, it's things on the airplane. On the airplane, if you've got steel that's magnetized a little bit, if you've got some magnets on board the aircraft, that's one reason why you don't put your headsets up on the top of the instrument panel. In addition to not scratching the windshield, you don't want to have it close to the compass because it'll affect the compass. And radios or any other electronic component in the aircraft that has a lot of current going through it. Next time you start the engine, watch the compass while you're cranking the engine. All those amps going through the starter wire will turn the starter wire into an electromagnet, and you'll see the compass move. But these are things that cause deviation, and the good news is that can get calibrated or corrected for, and that's why you're always going to have a compass correction card. Something like this. If you want to fly one direction, it might be off 1 or 2 degrees. And in fact, I think that the compass isn't going to be airworthy unless you have that compass correction card. Another thing you can check besides the compass correction card while you're taxiing is to see how accurate the compass actually is. Here's a diagram of Prescott Love Field, and here it's blown up a little bit. I find interesting for runway 21. Runway 210, this is the back of an IFR approach plate, and it's an IFR airport diagram, and it shows 209 degrees, 209.3. Actually, it says 209.3. So if we subtract that, we actually get 0.07 degrees difference. So it's really, really accurate. So you could be taxiing down taxiway Delta, and it should read the reciprocal of 209, and it's only off by 0.7 degrees, so you could essentially use the runway numbers in this case. However, all of the runways at the Prescott Airport aren't lined up with the magnetic compass quite so well. In fact, here's runway 30. Runway 30 is really 300, but it says that it's 304, 304.5 actually. It's actually 4.5 degrees difference. So if you were taxiing down taxiway Foxtrot, and of course here's the Embry-Riddle ramp, and you were checking your compass while you were taxiing, you should expect it to read 304.5, not 300. In fact, I have one really fun, one more fun example. Here's Tucson International, and here's runway 29 right. Runway 29 right is 290. And it says it's at 303.9, 303.9. So if we subtract, we get 9, 3, 10. It's actually off by almost 14 degrees, and they did that because it's across the freeway from the Air Force Base, Davis-Monthan Air Force Base, and they deliberately wanted to have different numbers. So I bet you $10 over at Davis-Monthan, they've got runway 30 right, and here they've got runway 29 right. But if you're taxiing along this taxiway Alpha, you do not want to be looking for 29 or the reciprocal of it, 290 or the reciprocal of it. You really want to be looking for 304 or the reciprocal of it. So if you really want the most accurate way to check your compass during taxiing, get a copy of the latest IFR airport diagram and see what the actual magnetic heading is you should have taxiing down that parallel taxiway. Fuel quantity indicators. There are DC systems. I know you're going to guess, and you're absolutely correct. You are right. Here is a DC fuel quantity indicating system, and it's identical in operation to a DC remote position indicating system, but this shaft coming out of the variable resistor has a float on it, so it's inside of a fuel tank, and as it goes up and down, the shaft gets rotated up and down, and it increases or decreases the resistance, and that will increase or decrease the amps, because we have a constant voltage from our DC bus. It'll increase or decrease the flux in our coil, and it'll increase or decrease the needle position. So on the test, be prepared to be able to draw a DC fuel quantity indicating system, which is identical to a DC remote position indicating system, which is identical, and label it, and is identical to a DC temperature indicating system. Capacitance system, it's a lot different. I think I'll draw my own instead. Got a fuel tank, and there's a couple of metal bars in here. Actually, 2 metal plates. It's a capacitor, and we're going to take each and go to a gauge in the aircraft that runs off of alternating current, and it's going to measure the capacitance, the ability to store electrons on one side and suck electrons off of the other side. And this ability is based on the distance between the plates, which doesn't change, but it's also based on what is in between it. So, for instance, if we have fuel in here, fuel doesn't have very much resistance compared to air, so less of them will get stored where there's fuel. And this gauge can actually tell how many electrons are stored, and it's based on how much fuel is in here. Now, here's what's interesting, is that if it gets hot, the fuel level will rise a little bit, but the total capacitance in here will stay about the same because it's based on how many molecules are in the middle here, not based on the volume. Or it could get cold, and the fuel level could go down and contract, but we still have the same number of molecules. So we're going to have the same capacitance. So the gauge in the cockpit isn't going to change. So that's a big difference between the capacitance system and the DC system. The DC system is measuring volume. If the fuel goes up or down, it's going to change. The capacitance system is measuring mass. So guess one which is more accurate. In fact, I've even seen some small business jets, small turboprops that actually have a primary DC system, and they actually have inverters to change the 28 volts DC into 28 volts AC. And one of the reasons is they need this alternating current to run the gauge so they can have a capacitance type fuel system, which is more accurate because measuring mass tells you how much energy you're really going to have, and measuring volume could be off. Hey, there we go. It's like I remembered that. Fuel flow gauges. There's a pressure type, and it's found on recips, fuel-injected recips. Like Cessna 172 is fuel injected in its recip, so it's got a fuel flow gauge, but it runs off of pressure. Now, this is the way it works. You got an engine with cylinders, with a propeller sticking out, and you're going to run fuel out to the engine. You're going to run fuel out to the engine. There's going to be a flow divider, and it's going to run the fuel right out to the cylinders right before the intake valve. And at that spot, there's going to be an injector. And that injector screws in to the cylinder. The fuel comes in, and there's this little tiny hole, a metered orifice. And the fuel's going to get squirted out based on how much pressure. The hole doesn't change size. So if we want to increase the fuel flow through that hole, we have to increase the pressure. Or if we want to reduce it, we have to decrease the pressure. So the fuel injection system is actually going to change the pressure going out here. If we tap off of this line and put a pressure gauge on it, then it would read in PSI, or inches of mercury. But instead of calibrating it in PSI, we're going to calibrate it in gallons per hour. And it's going to be really nice and cheap because we've got all the system except for this one extra fluid line and this gauge. So here is a 6-cylinder engine. You can see the flow divider. Fuel is going to come in, and it's going to go to 1, 2, doesn't show it very well, but there's 3, and there's 1, 2, 3 cylinders on this side, so this is a 6-cylinder engine. So we just have to measure that pressure. And here's one picture out of a twin-engine Cessna, and it says gallons per hour. It's probably hard to read, but it says gallons per hour. And here's 8 gallons per hour, 10, 12, 14, 16, 18, 20, 22, 24 gallons per hour. And I know it's really, really hard to read, but here it says 1.5 psi. And here it says 17.5 psi. So really this is a pressure gauge, but we've calibrated it in gallons per hour. It's not perfectly accurate, but it's pretty good. The downside is if the fuel nozzles get clogged up, then you'll have to run a higher pressure to get the same amount of fuel going into the engine. So this gauge, let's say you used to run it at about 18 gallons per hour to get 75% power at, say, 7,500 feet. But if the fuel nozzles, with that little tiny hole, if the fuel nozzles get clogged up a little bit, you're going to have to run higher pressure to get the same amount of fuel to squirt out. So you may actually have to run it at 19 gallons per hour, even though the exact same amount of fuel is going in. It's a higher pressure, but to get it through these clogged nozzles, you'll have to go to a higher pressure. So if the nozzles are clogged up, it's going to read a higher fuel flow than reality. Then there's the vane type fuel flow system. Let's see if I can draw it very well. This goes to the engine. This is from the fuel tank. And there's a vane in here that can move. And you'll notice that, let's try green fuel. Fuel comes in, has to go around the vane to get to the engine. Well, if we have to pump more fuel to the engine, this vane is going to move over. Well, if the vane's right here, we used to have this big of a hole to go through, and if the vane gets pushed over, we have a bigger hole. And if the vane gets pushed over here, it's an even bigger hole. So this shaft that this vane is on, as it sticks out, if we measure its position, say with a DC remote position indicator or an auto syn, which is an AC remote position indicator, every time this vane moves over, our gauge will move over as well. So this vane system is pretty simple. Problem is, it measures volume. It measures volume. So if the fuel is hot, it's going to read a little higher than normal. If the fuel is cold, it's going to read a little lower than normal. And we're going to say vanes are pretty good, plus or minus 3% accuracy. You typically find them on big recips and on smaller turbine-powered aircraft. The motorless mass impeller type, it's found on turbine-powered aircraft only, and it's great because it measures mass. It measures the mass of the fuel, and it doesn't matter whether it's hot or cold. We're going to spin this impeller around, so the fuel coming out of it is going to have a bit of a swirl. It's going to hit the inside of here, and it's going to push it around against springs wound in the opposite direction. If we measure how much this gets pushed around in degrees, it's going to tell us exactly how much mass got pushed into there. Force equals mass times velocity. If the velocity put into this fuel is constant, but we increase the mass, it'll increase the force, and this will get rotated farther over. And so all we have to do is measure how many degrees of twist this part has, and that'll tell us how much mass of fuel is going through it. You're not going to have to draw that on the test. Yay. And also, pounds per hour. You're going to see turbine engines, they're going to be calibrated in pounds of fuel per hour instead of gallons per hour. And hopefully that's also because it's measuring mass. Instrument range markings, you've heard most, if not all, of this stuff. Red radio line, of course, is don't ever exceed it. Here's a nice red radio line. Here's an Enstrom helicopter, and this is the rotor RPM, has a wide range, and then the engine RPMs on the outside, it has a small range, and so there's a red line here and a red line here. So interestingly enough, red line here and a red line here. So there's actually a minimum and a maximum on RPM, and of course never exceed might be don't go below that. I've also seen airplanes with red arcs. For instance, here's a fake RPM gauge, and let's just say for fun that there's a red line here at 2700 RPM, and it probably has some kind of a green arc in here, and there might be another green arc in here, which is normal operation. But there are very, very few airplanes I've seen where on the RPM gauge there's actually a red arc, and it's because the propeller engine combination has a vibration at certain RPM. So you can go through it to get to a higher RPM, and you can come down through it to get to a lower RPM. You just cannot leave the RPMs in that range. So there are some gauges that might have a red arc as well as a green arc. Of course, green arc is normal operating. Certain conditions / caution. Use caution, and you can only do it under certain conditions. I think I got a gauge here. Hey, typical airspeed indicator, of course. When can you be in the yellow arc under certain conditions? If there's no turbulence, you should use caution when you're doing it. And of course, well, I guess I left out a white arc. The only place I've seen a white arc was on, oh, that's a pretty lousy arc there. There we go. White arc is, let's see, max flap, extension, typically retraction as well, and operation, and of course, stall with, you know, all that stuff. I don't need to tell you that. So, you know about the connections and what to do in case of questions or suggestions on how to do things better. Thank you.